In the previous nugget, we discussed the block protocol of SCSI and how great it's going to be for the commands associated with reading and writing to a storage facility. Now, we know that one of the options for carrying these SCSI commands was Fibre Channel, and I promised you that we would go into much greater depth on this important storage area networking technology. So guess what? That time has arrived. Let's do it now in this nugget entitled Fibre Channel and more Fibre Channel. Now, as you might guess, this nugget's pretty darn important when it comes to SANs, and we've got lots to do as a result. I'll take you on a little history lesson, and we'll look at the topologies that have evolved through the years when it comes to Fibre Channel. Then, Fibre Channel is unique compared to local area networking technologies. We'll talk about all the different port types we have, many of which were invented by Cisco, and we'll talk about the wonderful world of addressing that we have in a Fibre Channel environment. Finally, I'll take you behind the scenes and we'll see exactly how a Fibre Channel storage area network is going to function. Do you remember the language of SCSI? We had that concept of an initiator and that concept of a target. Well, of course, we still have that in the Fibre Channel environment because remember, we are sending SCSI commands here in our storage area network. Now, the very first topology that was invented for Fibre Channel storage environments was the point-to-point topology. The initiator has a direct connection to a particular target device in that infrastructure. The initiator can obviously send commands directly to that particular target that's connected in that point-to-point connection. Now, obviously, the storage here functions as a dedicated server, and the initiator functions as a client. This does great for performance, it does great for security, but obviously one of the issues with this point-to-point topology for Fibre Channel networks is it doesn't give us scalability, right? This direct connectivity is a lot like that concept of directly attached storage that we've actually wanted to move away from for scalability concerns. So, we bring this up as a bit of historical reference, this point-to-point topology that is capable in a Fibre Channel environment. So in an attempt to address the scalability concerns presented by point-to-point topologies, the inventors of Fibre Channel networks decided they would do a Fibre Channel arbitrated loop. Yeah, the FCAL. And this Fibre Channel arbitrated loop would be obviously much more scalable than that point-to-point topology. But guess what? In actual practice, even though theoretically 120 devices can be connected in the arbitrated Fibre Channel loop, in actual practice you can only get about 12 due to performance concerns in this type of infrastructure. You see, because there's only one data path in this looped type topology, only one pair of devices can communicate at any one given time. So we have a loop type situation here where everybody's working with shared available bandwidth. There's latency concerns in this topology because these devices have to negotiate for control of the loop before they can send traffic. Is this sounding familiar to you? Does this kind of bring back the limitations and problems that we had in early token ring environments? It certainly should, because it is no coincidence. Another issue with the loop, just like we would find in a token ring type environment, would be how susceptible this environment was to a device failure. If we had one of our hosts, one of our initiators in the loop fail, we could have many, many different devices impacted by that failure. So kind of a second generation topology, if you will, the Fibre Channel arbitrated loop. Now, I bet you know where we're going in the third generation of topology that I'm going to show you right now. Yes, thank goodness the concept of the Fibre Channel switch was invented. In fact, when they did this, they really started talking about the fabric. Fabric equates to the concept of a storage area network when we're talking about a fiber channel environment. With the fiber channel switch, we can have the more efficient connectivity of fiber channel devices that we're looking for. And think about it. As you need to scale, you can go ahead and plug your fiber channel switch into another fiber channel switch, just as we would do in a local area network type of environment. So this third generation switched fabric topology is what we're so excited about today, and what Cisco certainly built upon with great inventions for fiber channel with their MDS line of storage area network equipment. Now, one of the things that's really interesting about fiber channel is our ports have different roles. They have different functionality, and they get these port names, right, that we need to get comfortable with. Let's start with the standard ports that we have in a fiber channel environment before any fancy inventions from an organization like Cisco Systems. All right, the first port that I want to talk to you about is the N port. And here we see an N port on a host that connects to the fiber channel environment. An N port is a node port. Arbitrated loop situation. Well, in this particular case, connecting to this old antiquated mess, we have an FL port. So this port right here is an FL port, and what the job of that port is, obviously, is to connect to that fabric loop in the topology. Sure enough, the ports that connect to that infrastructure get a special designation, and they are the NL ports. So here we have NL ports. These are node ports, but they are node ports in that special arbitrated loop type of topology that we can have with Fibre Channel. So take a good look here. These are the standard ports that we have in a fiber channel architecture. Our N ports, our fabric ports, our expansion ports, our FL ports for connecting to an arbitrated loop type environment, and then the node ports in there that are called NL ports in that special topology. But the engineers at Cisco Systems weren't just going to sit around and not make glorious inventions for the fiber channel infrastructure. So here we have a couple of Cisco MDS devices, and they can be connected by what are called TE ports. Yeah, the TE, the trunking expansion port. This Cisco invention allows MDS switches to expand on the functionality of those old E ports or expansion ports that we had in the classic fiber channel infrastructure. Thanks to the TE or trunking expansion ports, we can take advantage of virtual storage area networking. Can you believe Cisco did this? Yeah, capitalizing on the popularity of VLANs, Cisco invented the concept of a vSAN. These TE ports allow us to do quality of service over this particular trunk and special fiber channel traceroute features. So, when we have a TE port in our infrastructure, we're going to transmit frames in what is called an EISL format. This is going to contain the virtual storage area network information. Interconnected switches use this vSAN identifier in order to multiplex traffic from one or more virtual storage area networks across this same physical link. Again, this has parallels to our local area network environment, and that's why it makes it pretty darn easy for us to master. Now, another neat Cisco invention is an NP port, or a node proxy port. Remember we said we had our F ports on these devices and they would connect down to a node port for a particular host? Well, in Cisco environments, we can have an NP port, a node proxy port. And what this device is doing is it's allowing other N ports to connect through it for multiple physical N port connections through one F port. So this is a great enhancement for scalability in our Cisco-based fabric infrastructure. Now, what if we have a host device that wants to send in these tagged virtual storage area network frames? Well, some special port terminology for this environment. We would have a trunking fabric port, in this case, a TF port, and then a trunking node port. So a TN port would be on the device that has the ability to send those tagged frames for virtual storage area networking. Now, in our LAN environments, we often want to connect a protocol analyzer to the environment, and we use the switched port analyzer or SPAN feature for this. Well, this has a corollary in our fiber channel environments thanks to Cisco, and we can get into what's called an SD port. The SD port is a SPAN destination port in our fiber channel switched infrastructure. They can operate as a TE port. They can operate as a TF port. You get the idea. So these ports are extremely flexible and can automatically be initialized for a particular role when the interface comes up and determines what exactly is attached. By the way, I know we have covered a lot of terminology and concepts already, and we're very early in this particular nugget. This is definitely an area where we are learning a new vocabulary, aren't we? And just like you would do when learning a new vocabulary for a new language, you'll probably want to develop some aids to assist you. This would be a great area where flashcards, either traditional index cards or electronic flashcards, would come in very, very handy. Now, in our local area network environment, you're very familiar, I'm sure, with the concept of a MAC address. In fact, we looked at these in depth in the first of our 2 courses here for CCNA Data Center at cbtnuggets.com. Now, that's great. The MAC address is that unique identifier for layer 2 in our local area network environment. And sure enough, we have a similar methodology over here in the fiber channel world. They're called worldwide names. They are 64-bit or more commonly 128 bits in length, and they are indeed presented in hexadecimal. Now, there's 2 types of worldwide names that we need to be familiar with. There's the node worldwide name. This is one and only one address that uniquely identifies that particular node in the fiber channel infrastructure. Now, we know a lot of devices will have multiple Now, just like MAC addresses, these worldwide names are indeed hard-coded into our fiber channel devices. But there's another type of fiber channel addressing I want you to be aware of, and that's called the fiber channel IDs. Okay, you'll often see this as FCIDs. These are dynamically acquired addresses that are routable in our switch fabric. Remember when we were talking about the fiber channel arbitrated loop, and I told you that that had a limitation of 127 devices? That's because of the addressing scheme that is used for the dynamically chosen fiber channel ID. Through EF are actually available. Domains 00 and F0 through FF are reserved for use by internal switch services. Now keep in mind, even though through the mathematics of the situation here, there could be 239 switches in the fabric based on the fiber channel IDing system, in practice, the number of switches that you would get in your fabric typically is a lot smaller because of particular storage vendor built-in restrictions. Now, let me share a little bit about the Fibre Channel standards with you in case you are reading some of the literature and you come across these terms utilized. When they designed Fibre Channel, they did it in a 5-layered architecture. There's FC0, which defines the physical interface stuff like cabling, connectors, etc. There's FC1, which defines the line coding of signals. There's FC2, which indicates framing and flow control matters. There's FC3 for generic services that are required for fabric management. More on that in a moment. And then FC4, which is where we do our upper layer protocol mapping. Now, a big area here is the generic services that are going to need to be provided that would be really required for fabric management. These specifications outlined a name service, they outlined a login service, an address manager, an alias server, a fabric controller as it is known, a management server function, a key distribution server, and also a time server. Now, while a lot of Fibre Channel devices will provide many of these, like an MDS switch, for instance, from Cisco, it's important for you to realize that some of those functions can easily be provided by an external server. Now, remember at the beginning of this nugget, I promised you that we would peel back the curtains and we would take a look at Fibre Channel behind the scenes. Let's get into that now. One of the things a moment ago we learned that Fibre Channel needs is a Fibre Channel name server. And you know why. Yeah, we have all those crazy names. We have the Fibre Channel IDs, we have the port worldwide names, we have the node worldwide names. Certainly a more robust, a more complex naming architecture that we have in our LANs that just have the simple MAC address. It is the job of the Fibre Channel name server to go ahead and track all of this information for us, including some operational parameters that are used, like the upper layer protocol mappings and the classes of service that can be utilized in our Fibre Channel infrastructure. The Fibre Channel name server is a distributed database that our MDS switches implement in the Cisco infrastructure. You know what? Something else about this Fibre Channel name server process that's pretty interesting is it does what we call soft zoning. Now, what soft zoning means is that the worldwide node the most hysterical acronyms in all of computer networking. I love to say it. Say it with me. You ready? Floggy. Isn't that fun to say? Floggy. And if you love that, pretty soon we're going to talk about ploggy. That's right. So let's get into the details here of this Fabric login process. Now, a key element to this Fabric login process is the fact that the highest 16 addresses in our 24-bit Fabric address space are reserved. That's right. And this is going to be a comfortable concept for you if you are coming from the world of local area networking expertise. For instance, the broadcast alias is all Fs. If we have all Fs and then the address ending in an E, we have the reserved, well-known address for the Fabric login server. So there are plenty of reserved, well-known addresses in the Fibre Channel system that are going to facilitate processes like login and accessing key services in the storage area network infrastructure. So here you can see a conceptualization, right, of a couple of N ports and their respective F ports. Now, before these N ports can begin exchanging data in our fiber channel infrastructure, three things need to happen. You ready? First, the N ports must log in to their attached F ports. This process is indeed known as our fabric login or floggy process. Next, the N port must log in to its target N port. This process is known as the port login or ploggy process. And notice the abbreviation here is FDISC or FDISC. And finally, we have the discover port service parameter that can be used to verify the service parameters that exist for another N port, and this is abbreviated PDISC. Now let's transition to a topic that is so important, and we've been at this for such a while now. I need you to do something for me. Pause this nugget. Okay, please, trust me. Find the pause button. Pause this nugget. Stand up wherever you are right now. Stretch. Get re-energized. Check back into this nugget because we're about to cover something that is super, super critical and is going to impact your ability to understand a future nugget called Fiber Channel over Ethernet Explored. So, did you do it? Did you pause me? All right, welcome back. What we're going to do right now is discuss Fiber Channel flow control. You see, when they designed Fiber Channel, they said, hey, we're going to get a leg up on those silly guys over in the local area network world. Over there, packets can become dropped. That would be a disaster for those SCSI commands. Remember, the SCSI commands think they're over that highly reliable, short, parallel cable inside a machine. They are not going to tolerate any kind of packet loss. So what Fiber Channel engineers did was they implemented what is called a credit-based strategy for flow control within the particular technology. Specifically, here's how it works. The transmitter won't send a frame until the receiver tells the transmitter it can accept another one. What does this mean? It means that the receiver is always in control of this particular flow of information from the transmitter to the receiver. This eliminates the possibility of frames being lost due to things like buffer overruns, and it maximizes performance under very high load conditions in your storage area network. But wait a minute here. We know that the introduction of the switch fabric gives us a very scalable solution for Fiber Channel. But what about multiple paths? What about the potential for loops when we get a redundant environment built here with our MDS switches from Cisco Systems? Well, they borrow from other great concepts that we're used to. They created the to the various methodologies of implementing security that we can have in the storage area network environment. Let me just refresh you on that here as we wrap up this nugget on Fibre Channel. One of the things you know that we can do is zoning. And I'm not talking about that soft zoning that we looked at with our name service. I'm talking about really hard zoning your environment so that devices can't access other devices outside of their zone. But it turns out that zoning has tremendous scalability and manageability problems. So what did Cisco invent as an alternative? Yeah, we talked about it in this nugget, didn't we? The virtual storage area network. vSANs really bring tremendous benefits to an environment that had previously just been zoned. Something else to consider is how we protect our LUNs. When it comes to LUN protection, there are two techniques, remember. There is LUN masking and there is LUN mapping. You will understand where it fits in your modern data center architecture, and we will even build upon this material as we go throughout this course and many other courses together here at cbtnuggets.com. My name is Anthony Sequeira. I really sincerely hope that this has been informative for you, and I'd like to thank you for viewing.